7 million years ago, a profound transformation began in the heart of Africa, a change so radical it would eventually separate our ancestors from the rest of the animal kingdom. This was the dawn of bipedalism, the ability to walk consistently on two legs. While many animals can stand or hop briefly, humans are the only obligate bipeds among mammals. This wasn't just a simple change in posture, it was a total reconfiguration of the biological blueprint. Every step we take today is the result of millions of years of evolutionary trial and error, a journey that saw us rise from the forest floor to dominate the planet. In this deep dive, we peel back the layers of time to understand why our ancestors stood up, how their bodies adapted to this unstable way of moving, and what it cost them to become the upright walkers we are today. We must look past the modern concrete jungles and return to a time when the world was changing, and survival meant adapting to an environment that no longer favored the four-legged. This is the story of our greatest physical achievement, the first step toward humanity.
To understand where we are going, we must see where we began. In the late Miocene epoch, Africa was a continent of endless green. Our common ancestors with chimpanzees and bonobos lived in these dense, humid forests. They were masters of the canopy, possessing long arms, curved fingers, and flexible joints perfectly suited for brachiation and climbing. Their world was vertical, and their safety lay in the heights. However, environmental shifts were on the horizon. Tectonic movements and changing ocean currents began to alter the African climate, leading to a gradual cooling and drying. As the once contiguous forests began to fragment, our ancestors faced a choice: stay in the shrinking patches of green or venture out into the gaps. It is in these transitional zones, the mosaic environments of woodland and open space, that the first hints of bipedalism likely emerged. It wasn't a sudden leap, but a gradual adjustment to a world where the trees were getting further apart and the ground was becoming an unavoidable path between resources. Evolution does not move with purpose, but with necessity, and the necessity of travel was becoming paramount.
One of the most compelling explanations for the rise of bipedalism is the energy efficiency hypothesis. Moving on four limbs, specifically the knuckle-rocking style used by modern great apes, is incredibly taxing over long distances. As the African forests thinned, our ancestors had to travel farther between food sources. Studies comparing the metabolic costs of movement show that human walking is significantly more efficient than the quadrupedal movement of chimpanzees. By standing upright, we reduced the surface area of our bodies exposed to the harsh tropical sun and utilized a pendulum-like gait that saves energy with every stride. While a chimp might expend huge amounts of calories just to cross a few miles of grassland, a bipedal hominid could cover that same distance with a fraction of the fuel. This efficiency was a massive survival advantage. In a world where every calorie counts, being able to travel further for less meant more energy for reproduction, more energy for finding high-quality food, and a better chance of outlasting the competition. The shift to two legs was in many ways an optimization of the biological engine for long-range endurance.
Visibility and vigilance played a crucial role in the survival of the early bipeds. The Savannah Hypothesis suggests that as our ancestors moved into open grasslands, the ability to see over tall vegetation became a matter of life and death. By standing tall, a hominid could spot potential predators, like the ancient saber-toothed cats, from a much greater distance. This height advantage also allowed them to track migratory herds and locate distant watering holes. But there's another thermal benefit to standing upright that is often overlooked: thermoregulation. In the heat of the noon sun, a quadrupedal animal exposes its entire back to direct solar radiation. A bipedal hominid, however, presents only the top of the head and shoulders to the sun, while the rest of the body is kept in the cooler, moving air higher above the ground. This allowed our ancestors to remain active during the hottest parts of the day, when most predators were forced to rest in the shade. This thermal niche gave early humans a unique window of time to forage and move safely, effectively using the sun as a shield against the threats of the savanna.
Perhaps the most transformative consequence of bipedalism was the liberation of the hands. Once the front limbs were no longer required for locomotion, they were free to become the most sophisticated tools in the known universe. This free hands theory posits that the ability to carry things, food, water, infants, or weapons, was the primary driver of upright walking. Imagine an early hominid who finds a high-protein food source, like a carcass or a cache of nuts. A quadruped must eat on the spot, vulnerable to scavengers. A biped, however, can grab as much as possible and carry it back to a safer location or to share with their social group. This encouraged the development of food sharing and social cooperation, foundational elements of human culture. Free hands also paved the way for tool use. While other primates used tools, the constant availability of the hands allowed hominids to carry tools with them, refining them over time. This feedback loop between the hands and the brain accelerated cognitive development, leading to the creation of complex technology. Standing up didn't just change how we moved, it changed what we could do with the world around us.
To make bipedalism work, the human body had to undergo a radical anatomical restructuring, starting with the pelvis. In our ape-like ancestors, the pelvis was long and narrow, designed for the powerful leg movements needed for climbing. But to support the weight of the entire upper body over two legs, the pelvis had to become shorter and much broader. It evolved into a bowl-like shape that supports the internal organs and provides a stable base for the torso. This restructuring also changed the way our muscles work. The gluteal muscles, which in apes are primarily used for pulling the leg back during a climb, became repositioned in humans to provide lateral stability. Without this change, we would collapse to the side with every step we took. This bowl-shaped pelvis is the hallmark of a biped, but it came with a significant evolutionary trade-off, known as the obstetric dilemma. As the pelvis became more compact for efficient walking, the birth canal became narrower and more twisted, making human childbirth significantly more difficult and dangerous than in any other primate. It is a stark reminder that every evolutionary gain comes with a cost.
The changes didn't stop at the hips. The entire vertebral column had to be redesigned. While an ape's spine is shaped like a simple C-curve, the human spine has a distinct S shape. This double curve acts as a natural shock absorber, centering the weight of the torso directly over the hips and feet. It allows us to maintain an upright posture with minimal muscular effort. Furthermore, look at the foramen magnum, the hole at the base of the skull where the spinal cord enters. In quadrupeds, this hole is located toward the back of the skull as the head hangs forward. In humans, the foramen magnum has migrated to the very center of the skull's base. This allows the head to balance effortlessly atop the spine. This shift is one of the most reliable indicators for paleoanthropologists when determining if a fossil species was bipedal. Even a fragmented skull can tell us if an ancient creature walked upright simply by the position of this opening. The vertical alignment of the head and spine was essential for maintaining balance during the complex, multi-phase motion of the human stride.
The human foot is a masterpiece of engineering, uniquely adapted for the rigors of bipedalism. Our ancestors had feet with opposable big toes, much like our hands, which were perfect for grasping branches. But as we committed to the ground, the big toe moved into alignment with the other toes, providing a powerful lever for toe-off during each step. The foot also developed a complex system of arches, both longitudinal and transverse. These arches act as springs, storing elastic energy during the heel strike phase and releasing it as we push off. This makes our gait incredibly efficient for long-distance travel. Our knees also changed. The human femur angles inward from the hip to the knee, a feature called the valgus angle. This brings our feet directly under our center of gravity, preventing us from having to waddle from side to side like a penguin. Every time you take a step, your foot and knee are performing a delicate dance of weight distribution and energy conservation that took millions of years to perfect. We transitioned from a foot that could grasp to a foot that could propel us across continents.
The fossil record provides the physical evidence of this epic transition. One of the earliest candidates for bipedalism is Sahelanthropus chidensis, dating back to nearly 7 million years ago. Found in the Jurab Desert of Chad, this species lived close to the time of the human chimp split. While the remains are fragmentary, the position of its foramen magnum suggests it may have held its head upright. Then there is Auroran tugenensis, the Millennium Man, whose 6-million-year-old femur shows signs of weight-bearing typical of a biped. These early fossils suggest that bipedalism may have started much earlier than we once thought, possibly even while our ancestors were still spending significant time in the trees. These weren't humans in the modern sense, but they were the pioneers of the upright gait. They lived in a world of transition, and their bodies were the experimental laboratories of evolution. Each of these species represents a different version of the upright experiment, testing the limits of what a primate body could do on two legs in a changing African landscape.
Moving forward to 4.4 million years ago, we find Ardipithecus remidus, famously known as Ardi. Ardi is a revolutionary find because it challenges the idea that bipedalism evolved on the open savanna. Ardi lived in a wooded environment, yet her anatomy shows a strange mix of traits. She had a pelvis adapted for upright walking, but she still possessed a fully opposable big toe for climbing. Ardi proves that bipedalism didn't require us to leave the trees entirely. Rather, it may have begun as a way to move more effectively along sturdy branches, or to reach for fruit while standing. Ardi represents a mosaic stage of evolution, where the old and the new coexisted in a single body. She was neither fully ape nor fully human in her movement. Her existence suggests that the path to bipedalism was long and winding, with our ancestors maintaining their climbing abilities long after they began to walk on the ground. Ardi is the bridge between the canopy and the plains, a living testament to the complexity of the evolutionary process. Around 3.2 million years ago, we meet the most famous ancestor of all, Australopithecus afarensis, or Lucy. By Lucy's time, bipedalism was firmly established. Her pelvis, knees, and ankles are strikingly similar to ours, indicating that she was a proficient upright walker. However, her long arms and curved fingers suggest she hadn't completely abandoned the trees. The discovery of the Laetoli footprints in Tanzania, actual footprints of 3 individuals preserved in volcanic ash, confirms that Australopithecines walked with a remarkably human-like stride, including a clear heel strike and big toe push-off. Lucy and her kind were the masters of 2 worlds, utilizing the safety and resources of the trees while navigating the ground with ease. They were the first to truly embody the bipedal lifestyle, proving that this new way of moving was a successful and stable evolutionary strategy. For over 1 million years, Australopithecines thrived across Africa, their upright posture allowing them to exploit a wider range of habitats than any primate before them. With the appearance of Homo erectus about 1.9 million years ago, the transition was complete. Homo erectus was the first of our ancestors to have modern human body proportions, long legs and shorter arms. They were no longer climbers. They were dedicated, long-distance walkers and runners. This was the era of the persistence hunt. Homo erectus possessed a unique ability to run for miles in the midday heat, essentially outsweating and outlasting their prey. Their bipedalism had evolved from a way to save energy while walking to a way to become the ultimate endurance athlete. This capability allowed them to migrate out of Africa and colonize vast stretches of Eurasia. They were the first global travelers, and their legs were their primary mode of transport. The evolution of the Achilles tendon and the permanent arch in the foot during this period provided the spring needed for running. We had become a species defined by movement, capable of crossing continents one step at a time. The upright gait was no longer just about survival. It was about expansion and the conquest of new horizons.
However, we must acknowledge that our upright posture is an imperfect solution. The rapid shift from quadruped to biped has left us with a legacy of physical ailments. Because all our weight is supported by a vertical stack of vertebrae, humans are uniquely prone to back pain, herniated discs, and sciatica. Our knees and hips, bearing the brunt of every step, are susceptible to arthritis and injury in a way that 4-legged animals rarely experience. Furthermore, the reshaping of the pelvis for walking made the act of giving birth a complex and dangerous endeavor, requiring social assistance and leading to the high degree of infant dependency seen in humans today. Our babies are born early in a developmental sense because if they stayed in the womb any longer, their heads would be too large to pass through the bipedal pelvis. These are the biological taxes we pay for the privilege of walking upright. We are a work in progress, a species that has adapted to a vertical life, but one that still carries the echoes of its four-legged past in every ache and pain.
The story of bipedalism is not just a story of bones and muscles, it is the story of the human mind. By standing up, we freed our hands to create. By creating, we challenged our brains to grow. The feedback loop between walking, tool using, and social cooperation drove the dramatic expansion of the hominid brain. Standing upright also changed how we interacted with one another. It allowed for more face-to-face communication and the development of complex gestures. It fostered the need for cooperation, as mothers needed help with dependent infants and hunters needed to coordinate across distances. Bipedalism was the catalyst for the entire human project. It was the spark that ignited our technological and cultural evolution. From the first stone tool to the first painting on a cave wall, the freedom of our hands, granted by the strength of our legs, allowed us to reach for the stars. We are a species that looks up, not just because our eyes are high off the ground, but because our posture gave us the perspective to imagine a world beyond our immediate surroundings.
Today, we take our ability to walk for granted. It is so fundamental to our identity that we rarely stop to consider the 7-million-year epoch that made it possible. From Sahelanthropus to Ardi, from Lucy to Homo erectus, and finally to us. Each step in our evolutionary history was a triumph of adaptation. We are the survivors of a long lineage of upright walkers, the ones who successfully navigated the changing tides of climate and competition. Bipedalism is our heritage, a testament to the resilience and ingenuity of life. It is the reason we can travel the world, build civilizations, and explore the cosmos. As we look back on the dusty trails of the Pliocene and the lush forests of the Miocene, we see that our journey is far from over. We continue to evolve, to move, and to walk toward an uncertain but exciting future. So, the next time you take a step, remember that you are participating in a miracle of biology, a 7-million-year-old dance that defined what it means to be human. We stood up to see the world, and in doing so, we changed it forever.